So, we had talked about dispersion in single mode fibers last time, and we said that in single mode fibers you have material dispersion and waveguide dispersion. So, in the last class we quantified what that material dispersion is. Whenever we say dispersion, we refer to the delta tau, the delay, right. That delay because of the fact that the diffractive index is different, or delay because of the waveguide dispersion. The quantification is in delta tau. But last time we also quantified, we said that this delta tau is usually represented in units of picoseconds per kilometer nanometer. This much of dispersion, this is the spread for a kilometer of fiber per nanometer of your spread at the source, and that coefficient is what we call as the dispersion coefficient d, and that dm, dispersion coefficient, d material is dispersion, dm is referring to material dispersion coefficient, and that dm is nothing but we derive that it is minus lambda naught by c d square n by d lambda naught square. So, essentially if I know n versus lambda, I can in principle find dn first derivative and second derivative at a specific lambda, and from that I can calculate how much is the pulse spread. Now, we need to move on to waveguide dispersion, and as somebody had pointed out earlier, waveguide dispersion is because the fiber is a waveguide. So, you have several modes supported in the fiber. Each mode is travelling with different n effectives, and when your n effective is different, it is different for different lambda, and hence you have waveguide dispersion even in a single mode fiber, because if you have only one mode, there is only one n effective, but that n effective is also a function of lambda, and that gives you waveguide dispersion. Another way of visualizing this is the following. So, you had in one of the earlier assignments, you had calculated what is the mode field diameter at two wavelengths, right, in a single mode fiber. The fiber can be single moded at two different wavelengths, but what is the difference between the modes corresponding to the two different wavelengths? You will see that if your lambda 2 is greater than lambda 1, if I am looking at a higher wavelength, the mode spreads out to the cladding more than that in the core, right, because your n effective values are more towards the cladding value than the core value, right. So, this for instance you can say for a standard commercial single mode fiber, if this is the mode field diameter or representation of the mode at 1310, this could be something at 1550 nanometer. The mode corresponding to 1550 nanometer is always spread. Cutoff wavelength is closer to 1280 nanometer. So, 1310 is more guided, you may want to say, or more confined to the core, whereas as you go longer in wavelength, the mode actually spreads into the cladding. Okay. Now, the idea is that when you think of propagation of this over the fiber length, all these the entire intensity has to now propagate through the length of the fiber. Now, we are talking about a single mode fiber. Here again, the entire intensity has to propagate through the length of the fiber. Now, the speed experienced, effective speed experienced by this one and this one are different because their mode sizes are different. So, effectively the speed experienced by the two modes are different, and that is why we have waveguide dispersion, right. So, you say the energy distribution is decided by the wavelength, the effective index is different for different wavelengths, and so different wavelengths will take different times, and so you can quantify a waveguide dispersion. So, how do we quantify this? We can start from a single mode fiber, and the most holy relation, the universal relation for a single mode fiber is your B versus V, right. So, you remember V is omega by C A square root of n1 square minus n2 square. This is the V number for a fiber, and the other normalized parameter that decides propagation is the B number. And what is the range of values for B number? 0 to 1, and every B has every V has a unique value of B. And remember, we are talking only about single mode fibers, which means that the V number is always confined between 0 to 2.4048, the first 0 of the Bessel function. first order Bessel function. So, your B we define as, do you remember the definition of B? B is what finally we said is the unknown variable in our transcendental equation. This is beta square minus n2 square, n1 square minus n2 square. Yes, there is a beta square by k naught square, because that is a normalized refractive index. All right. So, B is given by this formula, and we are going to the goal is to find out how delta tau can be derived now. Now, what is delta tau? Dispersion because of the waveguiding nature. Now, when you want to say dispersion, like in material dispersion, we are going to find out tau, which is the time of propagation, and then you have to find out what is delta tau, differential of that time, because of this. So here I know that beta is a function of lambda, and so B becomes a function of lambda, and so I want to find out what is the propagation constant or the group velocity as a function of lambda, right. So, that is the goal. So, to do that I am going to do a slight shortcut here. We are going to do beta by k naught minus n2 times beta by k naught plus n2 divided by n1 minus n2 times n1 plus n2, okay. And we know very well that beta by k naught is your n effective, and this n effective is a number that lies between it is always less than n1, but it is always greater than n2, and the difference between n1 and n2 for a single mode fiber is very, very small, right. So, what I can think of doing is that the sum of these two, beta by k naught plus n2 and n1 plus n2, I can approximate that the numerator and the denominator are almost identical, okay. But the differences I cannot ignore, because the ratio of the differences is what is going to give you the most contributing value for B, okay. So, this becomes, this I am approximating as beta by k naught minus n2, so that I get an analytical relation for delta tau, okay, n1 minus n2. Now, beta is a number that is going to be dependent on lambda here. So, I am going to write beta in terms of B. So, this becomes beta by k naught, just algebra, equal to B times n1 minus n2 plus n2, or my beta is equal to k naught which is omega by c times n2 plus b times n1 minus n2. So, I got my propagation constant, okay. Now, remember what is our goal? We want to find out the time of flight, or time taken to reach the other end. So, I need to worry about velocity. Now, do I look at phase velocity or group velocity? I look at group velocity, and I know last time we discussed 1 by Vg is equal to d beta by d omega, which means I can calculate the inverse of the group velocity by differentiating this with respect to omega, and that is easy because so which are the variables here which are dependent on omega? So, there is a first term here, omega c is of course dependent on omega. Is n2 dependent on omega? In principle, yes, material dispersion says that n2 is a function of omega, but right now we are not talking about material dispersion, we are talking about waveguide dispersion. So, here I am going to say that n1, n2 are independent of omega, considering n1, n2 as independent of omega. Because I have already considered the dependence of n1 n2 of omega in my material dispersion, I do not have to do it in the waveguide dispersion, right. So, I am going to consider n1 as n2 as constants. Then what else is a function of omega here? B is a function of omega, because B is a function of V and V is a function of lambda, and so V becomes a function of omega, right. So, I have to differentiate such that the first term is 1 by C. Can you do this differentiation? plus omega by c, differential of n2 is a constant, plus n1 minus n2 times. Now, how do I write the differential of b versus omega? I do not have a direct relation between b and omega. I know that b is a function of v and v is a function of omega. So, I write it as db by dv and dv by d omega. So, I have this as my 1 by Vg. Now, can I simplify this? Well, there is no omega c plus, it is omega c times actually. So, before simplifying, let us calculate what is dv by d omega. I have v as a function of omega. So, dv by d omega, first derivative is just 1 by c a root of n1 square minus n2 square. A is core radius, that is not going to be dependent on omega, and n1 and n2 I have already said it is independent of omega. So, my dv by d omega is nothing but v over omega. So, I can substitute this as 1 by c n2 plus b times n1 minus n2 plus omega by c n1 minus n2, dv by d omega is v over omega, and I still have db by dv, okay, of which my omega cancels and 1 by c is common again. So, this becomes 1 by c n2 plus v times n1 minus n2 plus 1 by c is out, n1 minus n2 times v times dv by dv, and I can take n1 minus n2 common between these two terms, and I can write this 1 by Vg as 1 by c times n2 plus, I can take n1 minus n2 common, and the first term has a b and the second term has v dv by dv. So, my propagation time is going to be, if I say length is L is the length of the fiber, total length of the fiber, L divided by Vg. So, this is nothing but L by C n2 plus n1 minus n2 times b plus v this. I could put out L by C n2 out and then write it as 1 plus, I can approximate this as delta. What was delta? n1 minus n2 divided by actually n1, but here you are approximating it as n2. It is not going to be very different as what you are saying. Delta times b plus v db by dv. So, this is the time taken for a source or a specific pulse to propagate through the fiber. But now we are interested to know how much is the, so if my pulse had a certain delta omega spread, what is the time delay between this component and this component is what we are trying to figure out, right. So, that is why our dispersion will now be delta tau is equal to d tau. Again, while writing dispersion, we want to maintain the unit of the same thing, picosecond per kilometer and nanometer. So, instead of delta omega, we talk about delta lambda spread, right. So, if the source has a spread of delta lambda, then what is the difference between the time of flights of the two extreme lambdas that I have in my source, that is my delta tau. Okay. So, my delta tau is d tau by d lambda delta lambda, where delta lambda is now my spread in the source. All right. Now, this is a question of differentiating this once again, because I have to differentiate with respect to lambda. So, N2L by C is a constant. I do not have any contribution because of the first term. I will have only delta, which is a constant. Now, B, it is a function of lambda. So, to simplify, what I can do is I can write this as d by dv of bv, right. If I expand d by dv of bv, I am going to get b plus v db by dv, which is what I have, just for simplification. Okay. So, now if I take the differential of this d square by dv square of bv times dv by d lambda, because that is a function of lambda. My explicit dependence of bv is on v. So, if I were to differentiate, I will differentiate with respect to v again, but then the implicit dependence of bv is on is through of b is to lambda is through v. So, I will do a dv by d lambda. That is how I will do a differentiation with respect to lambda. So, but now what is v by dv by d lambda? I know v is equal to omega by c, which is 2 pi by lambda a root of n1 square minus n2 square. So, dv by d lambda is going to be minus 1 by lambda square 2 pi a root of n1 square minus n2 square, which is constant. So, this I can write it as minus v over lambda, all right, because it is just the same as lambda, but there is multiplication by minus 1 by lambda. So, here I can substitute this as N2L by C delta d square by dv square of bv times minus v over lambda. So, I get delta tau as minus of N2L, of course, there is a delta lambda I am missing here, this delta lambda I have to keep multiplying. N2L by C delta delta lambda by lambda. Remember, this delta is not, so this delta represents N1 minus N2 divided by N2 for me, right. Delta lambda by lambda, and what else is there? V times d square bv by dv square. This is because of the waveguide dispersion. Putting a subscript w to indicate that this is only because of the waveguide dispersion. So, if I were to now define a dispersion coefficient in terms of picosecond per kilometer nanometer, what should that be? This will be in picosecond per kilometer nanometer. What should that be? I should divide it by the length, I should divide it by delta lambda. So, I will have minus N2L by C delta 1 by lambda V d square bv by dv square. So, how does one go about calculating this? You have to quantify this now. So, where does one start with? Let us say I have a source of center wavelength some 1550 nanometer and I have a delta lambda spread of 2 nanometer. What information do I require now to find out the waveguide dispersion? I will of course need to know N2. I need to know, of course, oh sorry, there should not be a length here, right, because this is in picoseconds per kilometer nanometer. So, it has to get divided by the length and it has to get divided by the lambda spread. These are typical units in which, of course, you can write it in second per meter square also, but the typical units that are referred to in data sheets is this, because the orders of magnitude of delta lambda we are talking about is in nanometers, orders of magnitude for lengths are in kilometers, and the orders of dispersion are in picoseconds. So, how do I now go about calculating this? Let us say I have a source at 1550 nanometer and it has a spread of 2 nanometer. I want to know the waveguide dispersion. So, what else do I need to know? I need to know some information about the fiber. What information do I need to know? I need to exactly know the core index and the cladding index, because you have a delta and you have an N2 in the system. So, I need to know the core index, I need to know the cladding index. What else do I need to know? I need to know what is the V number, which is here, and not just that, I need to know the second derivative of the product BV at that particular wavelength. How do I get that product BV at that particular wavelength? So, how do I first do the second derivative? How do I get to that point? So, you have to go back to the universal BV curve. Remember, we had plotted for the fundamental mode B versus V is universal. We had some curve like B versus V was something like this. Fundamental mode did not have a cutoff, it was something like this, right? And the first cutoff for the first mode was what? 2.4, right? So, you are interested only in this region because you are talking about the waveguide dispersion for a single mode fiber. So, in that B versus V curve, universal curve, now you find out for the lambda that you are using, for the fiber that you are using, what is the V number. So, you locate your V number, and then at that point you do not want B actually, you want the second derivative of the product BV, which means from this curve you have to find the product BV, find its first derivative with respect to V, find its second derivative with respect to B, whatever that curve is, at that point you should find out this value, substitute, that is how you quantify.